A warm welcome to all of you. In the previous class, we had spoken about the direct synthesis and indirect synthesis. In indirect synthesis, we have spoken about the phase lock loop. And today, I'm going to talk about direct digital synthesizer. So, as the name suggests, as the name suggests, digital synthesis, so there is certain amount of storage, there is a flexibility due to some programming capability, and you will see that in the forthcoming slide. So direct digital synthesis or direct digital synthesizer works on the principle where there is storage in a lookup table, and this storage is in the digital domain, and there is a phase accumulator which stores this information in the form of a lookup table. The accumulator will pick up various points from the sine wave, that is from the lookup table, and will apply it to a D to A converter which converts it into analog domain. Obviously, over time, these points will make a sine wave. So there is a D to A converter whose output is shown here in the time domain, and the reconstruction filter which converts the output of the D to A converter into a high quality sine wave is shown in the time domain response, which is further given to a limiter which squares the output and gives you the desired clock signal. In the frequency domain, the response expected from the D to A converter is that of a sinc function. This is an ideal frequency domain response, and you can find the harmonics also present. After it has gone through the reconstruction filter, the harmonics are taken out and we are left with the fundamental frequency, following which then passed through a limiter. You are left with the odd harmonics in the response. Now, in reality, in the real world system, this sinc function is not free from spurious components which are present here, which may not be filtered by the filter, and they will still persist. Then, after through the limiter, after passing through the limiter 2, you will find that these spurious components are present, which will cause a lot of jitter and noise in the clock signal. Here you see a flexible DDS system because it has a capability of programming it and sending the serial byte load register data into the parallel delta phase register, which contains the tuning word M. The phase accumulator uh, has a register which contains the lookup table. There is input given from the serial byte load register, which will in turn program the delta phase register, and that will indicate to the phase register which contains the uh, phase wheel uh, to pick up points as it moves around. So it moves around. That contains the lookup table where a lot of information of phase and amplitude is stored, and depending upon the tuning word, this phase register will then pick up points at various phase locations to give you this amplitude response. Then the phase to amplitude converter will give rise to a sinusoidal kind of response, which is then further given to the DAC. Then the DAC output is given to the low pass filter, and that is the reconstruction filter, to give a then further give it to the reconstruction filter, the limiter, to generate the clock signal. So this slide shows you the signal flow through the DDS architecture. You can see that the phase accumulator has a reference clock like the DAC, and the tuning word which is programmed into the delta phase register then helps the phase accumulator to look for certain points in the phase wheel, that is the lookup table which is stored in the phase accumulator. So you can see that this M is the jump size, and this jump size, if you notice here, has a relation. So if I'm looking for a certain output frequency and FC is the clock frequency, so that's the highest limit, I would be looking for something which is lower than the clock frequency. Of course, there is a limit for that too, a higher limit and lower limit. So I would be taking M, which is nothing but the fraction of the clock frequency. And of course, I have this portion 2 raised to n, which stands for n is the size of the phase accumulator, resulting into 2 raised to n locations. So there are 2 raised to n locations where it contains data of phase and amplitude stored into the lookup table. And if I choose to have M, which is nothing but the jump size, I can choose to have any amount of jump size depending upon the requirement of my frequency. So I'll be talking about it in detail. So you have understood that N is the size of the phase accumulator word length, or the size of the phase accumulator, resulting into 2 raised to n locations where of the lookup table, which contains the phase and the amplitude information. Then the phase accumulator, which has received the tuning word, M tuning word, from the programmer, has selected certain points on the phase wheel, and it has resulted in this type of reading out of the phase and the amplitude information, which is then given to the phase to the amplitude converter to give you the envelope kind of response. Then the DAC gives you the analog domain response of the sine wave, which when filtered out gives a high quality sine wave. So I was talking about the DDS design phase accumulator. So the n bit, so to determine the frequency, the DDFS system has a 2 raised to n bit phase accumulator and a reference clock. This phase accumulator can address up to 2 raised to n different ROM locations or samples. So, what is going to be the frequency of resolution that I would get from this synthesizer? It depends upon the bit size, the size of the phase accumulator. Of course, it depends upon that. So you can see this is the phase wheel, and you know that a sinusoid has a phase response. So if this is the vector which is rotating, it completes 360 degrees and it's back in its position. So the amplitude, this is the way the phase would rotate. At the same time, the amplitude would form a sinusoidal response. So what happens is this phase wheel information, or 2 raised to n locations or samples which are stored in the phase accumulator, have to be used to generate all frequencies of interest that we are interested in. Yet there is going to be a lower limit and a higher limit. So there is going to be a cap on the lowest frequency and the highest frequency. So the lowest frequency would mean that I have moved from this point to the adjacent point where a lot many clock cycles uh, have have been have gone by, and I am still moving from, say, this point to the next point. And the highest frequency would mean that I have taken a lot of jumps across these points and I have reached this point quickly. So if I take small steps, I take longer time to reach. So the frequency is lower. And if I take larger steps, I reach quickly. So the frequency of resolution Fr is given by the clock frequency divided by 2 raised to n ROM locations. So there is a problem in the book by Jack Smith. What will be the frequency resolution if we have a 32-bit accumulator and clock of 10 megahertz? So if you put in 2 raised to 32 over, this to be 10 megahertz over 2 raised to 32, the answer you get is 2.33 millihertz. So the resolution, this is the phase resolution which corresponds to frequency resolution. So these are points on the phase wheel which represent the phase resolution, which is theta equal to 2 pi f, and so this is the resolution that you would get in case of this problem. So the frequency of resolution and the lowest frequency would be the same. So the lowest frequency that I would get from a DDS will be equal to the resolution frequency. So what about the upper frequency? This equation still holds good, and we have understood that the frequency that I desire, the F naught, follows a relation with the clock frequency, which is inversely proportional to the size of the phase accumulator, and these are the jumps, the jump size, and you can also say the number of samples that you would take to achieve your output frequency. If you realize this, so if I take a larger jump, I'll get the higher frequency, and so if I take a low frequency, I can go as low as m equal to 1 and have a low frequency, and that means that my so if I take m equal to 1, I get a low frequency which is as good as the resolution frequency, and if I increase this m to a larger value, I would get a higher frequency. However, there is a limit. I cannot increase it very much higher. So at least 4 or 5 for higher frequency, which would give me FH. So the number of samples that I would take. And okay, so what do you notice here? That the desired frequency is related directly to the clock frequency and inversely proportional to the size of the accumulator. So it seems to us that if the size of the accumulator, so where I have interchangeably used a small n or a capital N, it means the same. So if I increase the size of the accumulator, it means that my frequency, output frequency would reduce, or rather I would get a very low frequency limit. That is to say, my resolution frequency will increase. So it seems to us that increasing the size of the phase accumulator will give us a very good, very low resolution frequency. Yet there are some pitfalls here. So it looks like increasing the size gives us a good resolution, a low resolution frequency, yet the noise power which is related to the size of the accumulator, it will worsen because it follows a linear relationship here. So the noise power will increase. All right, so you see that we cannot do that, and this has to be taken into consideration, and this noise power is mainly due to the digital to analog converter, which also uh, requires a clock signal, and it will also introduce some harmonic noise, and it will create a lot of noise in the clock signal, which is not a good thing. So the memory size, so there is going to be a problem. So how do we decide on the memory size? Because the memory size, if you are designing a DDS, you would want to generate a certain band of frequencies from FL to FH, and you are to decide uh, whether or not to take a certain number of bits as the size of the phase accumulator. So all that you need to understand is that you need to take into consideration the noise power. So the power budgeting comes into picture. So you're looking for a certain amount of spectral purity, and that has to be taken into consideration. So look at this example given in Jack Smith. Design DDFS to cover the frequency range from 0 to 10 kHz with a frequency resolution of at least 0.01 Hz. The spectral purity is to be at least 40 dB. So what you notice here is that if we look for this kind of spectral purity, and we put in this formula, uh, if we take 7 bits, then we would get around 42 dB as a noise power. An addition of a sign bit means 8 bits would be sufficient. But if you go in for this formula where you choose the size, uh, here using this formula memory size, you will find that around 26 bits are required, and it's very beautifully explained in the book as to why 26 bits are not required and just about 8 bits are sufficient. So we are not trying to save all the points, but these are all samples, and the D to A converter would do the rest of the job. Hence, we do not actually need to have all the points being stored. So 8 bits are sufficient. So the disadvantages of the DDS are as follows, that the upper frequency, the higher frequency limit has the output waveform which will consist only 4 samples, and so it will not look much like a sine wave unless the harmonics of the fundamental frequency are removed by a low pass filter. So this filter should have a bandwidth slightly greater than the higher frequency limit, and hence it requires a steep attenuation that causes a group delay. As you know, you have studied filters. The next point is the main drawback of the DDS is that it is limited to relatively low frequencies because the because of the D2A converter. The upper frequency is restricted by the maximum possible clock frequency and the settling time of the D2A converter. In addition to this, as we you go very high with frequencies using the DDS, the power consumption becomes quite large.